Is the sun really a giant ball of fire? At first glance, the answer seems obvious. Every morning it rises in flames of gold and white, pouring heat and light across the sky. It blazes with such intensity that no eye can stare at it for more than a moment. It warms oceans, ignites winds, and paints the world in shadows and color. For as long as humanity has existed, the sun has looked like fire, an eternal inferno suspended above the earth. But appearances in the universe are often deceptive. Fire, as it exists on Earth, is a fragile thing. It consumes oxygen. It feeds on fuel. It flickers, dances, and dies. A flame is chemistry in motion, atoms rearranging themselves in a brief and violent exchange of energy. Every campfire, every candle, every raging wildfire is bound by the same limits. It must breathe, it must eat, and eventually it must go out. Yet the sun has burned for over 4.5 billion years. It has shone through the rise and fall of continents, through the extinction of ancient species, through ice ages and volcanic ages alike. It illuminated a planet long before life crawled onto land, and it will continue shining long after humanity is gone. No fire could survive that long. No chemical flame could endure on such a scale. So if the sun is not burning like fire, what is it doing? To answer that question is to step away from the familiar world of oxygen and fuel and into a realm where matter itself becomes energy, where gravity crushes atoms together, and where the rules of everyday experience dissolve under unimaginable pressure. The sun is not a fire. It is something far more profound. Deep within its heart, the sun is a vast, self-sustaining engine powered by nuclear fusion, a process so extreme that it cannot occur naturally anywhere on Earth. Fusion does not require air. It does not rely on combustion. It does not consume fuel in the way flames do. Instead, it reshapes the very building blocks of matter. At the center of the sun, gravity reigns supreme. The sun contains more than 99% of all the mass in the solar system, and that mass presses inward relentlessly. Layer upon layer of plasma is squeezed tighter and tighter, until, at the core, pressure becomes almost impossible to comprehend. Temperatures soar beyond 15 million degrees Celsius. Under these conditions, atoms can no longer remain intact. Hydrogen, the simplest and most abundant element in the universe, becomes the sun's raw material. Each hydrogen atom consists of a single proton, carrying a positive electric charge. Normally, protons repel each other. Their like charges push them apart, making fusion seem impossible. But in the sun's core, gravity forces them so close together that this repulsion is overwhelmed. When hydrogen nuclei collide with enough force, something extraordinary happens. They fuse. Two protons are pressed together until they merge, forming a new element, helium. But the helium nucleus weighs slightly less than the combined mass of the hydrogen nuclei that created it. That missing mass does not vanish. It is transformed into energy. This is the meaning hidden inside Einstein's famous equation, E equals mc squared. Mass and energy are not separate things. They are different expressions of the same fundamental reality. In the sun, a tiny fraction of matter is converted directly into pure energy, released as light and heat. Every second, the sun converts millions of tons of mass into radiation. And yet, despite this staggering output, it remains stable. It does not explode. It does not collapse. Gravity pulling inward is perfectly balanced by energy pushing outward. This equilibrium allows the sun to shine steadily, day after day, epoch after epoch. The light that leaves the sun's core does not race instantly into space. Instead, it begins a long, slow journey outward. Photons are absorbed and re-emitted countless times as they struggle through dense layers of plasma. What will eventually emerge as sunlight may take tens of thousands of years to escape the sun's interior. By the time it reaches the surface, the energy has softened, stretched into wavelengths our eyes can see. What began as gamma radiation becomes visible light, warmth on skin, and the quiet glow of a sunrise. The sun's surface appears calm from a distance, a smooth, glowing disk suspended against the blackness of space. But this tranquility is an illusion. Beneath the surface, vast currents of plasma churn and rise like boiling water. Hot material ascends, cools, and sinks again in colossal convection cells larger than entire continents. Dark blemishes known as sunspots drift across the surface. They are cooler regions, shaped by intense magnetic fields that twist and tangle like invisible storms. Sometimes these magnetic forces snap, releasing explosive bursts of energy. Solar flares erupt, blasting radiation across space at the speed of light. Prominences arch thousands of kilometers above the surface, glowing ribbons of plasma held aloft by magnetism. Occasionally, the sun hurls billions of tons of charged particles outward in coronal mass ejections, vast clouds capable of disrupting satellites, power grids, and communication systems on Earth. Despite its apparent constancy, the sun is alive with motion and violence, and yet life depends on its restraint. Earth orbits at a distance where the sun's energy arrives in just the right amount. Too close, and oceans would boil away. Too far, and the planet would freeze into lifeless ice. This delicate balance allows liquid water to exist, a rare and precious condition in the universe. Every breath, every growing leaf, every beating heart traces its energy back to the sun. Plants capture sunlight and store it as chemical energy. Animals consume that energy, passing it along through the web of life. Even the fossil fuels buried beneath Earth's surface are ancient sunlight, preserved across deep time. The atoms in human bodies were not created here. They were forged in stars long before the sun was born. But it is the sun that arranges them into living systems, that powers the fragile chemistry of life. For ancient civilizations, the sun was more than a source of light. It was a god. In Egypt, it sailed across the sky in a golden boat. In the Andes, it was worshipped as Inti, the divine ancestor of emperors. Across cultures, the sun became a symbol of order, rebirth, and authority, a celestial presence upon which all things depended. Science did not diminish this reverence. It transformed it. By uncovering the sun's true nature, humanity gained not mastery over it, but perspective. Understanding fusion revealed that the sun is not eternal. It has a life cycle. One day, billions of years from now, its hydrogen fuel will begin to run low. The balance between gravity and energy will shift. The sun will change. But for now, it remains steady, a cosmic engine burning not with flame, but with the quiet, relentless power of physics itself. A star not of fire, but of fusion. And this understanding is only the beginning. What is the sun? How does it burn? Is the sun really a ball of fire? The sun's light appears effortless, as if it simply exists, pouring endlessly into space. But beneath that calm glow lies a complex interior, layered like a living organism, each region playing a precise role in sustaining the star's long life. At the very center lies the core, a region so dense and hot that ordinary matter ceases to behave as matter at all. Here, atoms are stripped of their electrons, forming a state known as plasma, a seething ocean of charged particles. Gravity presses down with such intensity that every cubic centimeter weighs more than gold. Time itself seems to slow in this crushing environment, where nuclear fusion proceeds at a measured, controlled pace. Surrounding the core is the radiative zone, a vast region where energy moves not through motion, but through radiation. Photons born in the core begin their long ascent here, colliding endlessly with charged particles. Each collision changes their direction, scattering them in random paths. Progress is agonizingly slow. A single photon may take thousands, even hundreds of thousands of years to traverse this zone, wandering like a traveler lost in a dense fog. Above the radiative zone lies the convective zone, where energy finally begins to move more freely. Here, heat causes plasma to rise toward the surface, cool, and sink again in enormous circulating currents. These convection cells churn continuously, shaping the sun's surface patterns and feeding its magnetic field. What appears smooth from Earth is, in reality, a restless sea of motion. The visible surface, the photosphere, marks the boundary between the sun and space. This thin layer, only a few hundred kilometers thick, is where sunlight finally escapes. It glows at roughly 5,500 degrees Celsius, cooler than the interior, yet still hotter than anything humans have ever created. Granules ripple across it, bright, short-lived cells formed by rising and falling plasma. Above the photosphere lies the chromosphere, a realm of crimson light visible during eclipses. Here, temperatures begin to rise again, defying intuition. And above that, stretching millions of kilometers into space, is the corona, a ghostly halo of plasma hotter than the surface itself, reaching temperatures of several million degrees. The corona's heat remains one of solar science's greatest mysteries. Somehow, energy from the sun's magnetic field is transferred upward, heating this tenuous atmosphere to extreme levels. The corona extends far beyond the sun's visible edge, blending into the solar wind, a continuous stream of charged particles flowing outward through the solar system. This wind shapes invisible bubbles around planets, carving magnetic shields and sculpting space itself. Earth's magnetosphere deflects much of this radiation, protecting life below. Without it, the solar wind would slowly strip away the atmosphere, as it once did on Mars. The sun, though steady on human timescales, breathes in rhythms of its own. Its magnetic field waxes and wanes in cycles lasting about 11 years. During periods of heightened activity, sunspots multiply, flares erupt more frequently, and the corona grows more turbulent. During quieter phases, the sun settles into relative calm. These cycles ripple outward, influencing Earth in subtle ways. Increased solar activity can intensify auroras, painting polar skies with curtains of green and violet light. At times, it can disrupt radio signals, damage satellites, and challenge modern technology. Even now, humanity remains vulnerable to the moods of its star. And yet, the sun is remarkably gentle, at least by cosmic standards. Compared to other stars, it is modest in size and temperament. It is neither a raging blue giant nor a volatile red dwarf prone to violent outbursts. It is a yellow star, middle-aged and stable, burning its fuel carefully. This stability is no accident. It is the reason Earth has enjoyed billions of years of relatively constant conditions, allowing complex life to evolve. Elsewhere in the universe, stars burn hotter and faster, exhausting their fuel in mere millions of years. Others flicker unpredictably, bathing their planets in deadly radiation. The sun occupies a rare middle ground, a balance between power and patience. Long before science uncovered these truths, humans sensed the sun's importance instinctively. Stone monuments aligned with solstices, calendars tracked its movements. Agriculture depended on its cycles. Empires rose and fell according to its predictability. To ancient eyes, the sun was eternal, unchanging, a divine constant in a chaotic world. But modern understanding reveals a deeper, more humbling truth. The sun was born. About 4.5 billion years ago, a cloud of gas and dust collapsed under its own gravity. As material spiraled inward, pressure and heat increased until fusion ignited. The sun entered the main sequence of its life, a long, stable phase that will last roughly 10 billion years in total. Today, it stands about halfway through that journey. Far in the future, when hydrogen in the core becomes scarce, fusion will slow, gravity will gain the upper hand, the core will contract and heat up, igniting fusion in surrounding layers. The sun will swell into a red giant, expanding beyond its current boundaries. Mercury will vanish. Venus will be consumed. Earth may be scorched, stripped of oceans and atmosphere, or swallowed entirely. Eventually, the outer layers will drift away into space, forming a glowing planetary nebula. What remains will be a white dwarf, a dense, fading ember, slowly cooling over trillions of years. Even then, the sun's influence will persist. Its remnants will enrich the galaxy with heavier elements, contributing to future stars, planets, and perhaps life elsewhere. In this way, the sun is both creator and recycler, a participant in a vast cosmic cycle that stretches far beyond any single system. Every star tells a version of this story. By understanding the sun, humanity gains insight into the workings of galaxies, the origin of elements, and the fate of matter itself. The sun is not unique in function, but it is unique in proximity. It is the only star we can study in intimate detail, the only one that shapes our daily existence. Its light connects the infinitesimal to the infinite. It links atomic interactions to planetary climates, nuclear forces to biological rhythms. It reminds us that the universe is not distant and abstract, but present, woven into every moment of life. The sun is not a ball of fire. It is a fusion-powered star, a controlled explosion held in balance by gravity, a lighthouse in a dark galaxy. It is ancient, yet temporary, violent, yet nurturing, simple in composition, yet profound in consequence. And still, the question lingers, not as a misunderstanding, but as a reflection of wonder. Because even knowing what it truly is, when the sun rises and floods the sky with light, it still feels like fire.